Okay, guys, so I hope everyone watched the lecture about the safe operating system Redleaf, right? It's very shy, but wait, so it's actually kind of cool. So Redleaf is an interesting system for real. So it's not that I'm saying that it's absolutely in the future of operating systems, but it's an interesting step, at least in some direction. So do we understand how it works? Just ask. What does it mean to implement isolation in a programming language? So what do we do to achieve isolation between, what is a process in a programming language? Anyone? Gary, tell us what is a process in Redleaf? How do you implement a process in Redleaf operating system? You don't know? That's bad because well, let me remind you. So like remember I said that in Redleaf, a process is very similar thing as in a regular operating system. You just write a main function in Rust, and whatever executes in this main is your process, right? I agree. Why is it isolated from the rest of the system? How do we build an isolation boundary? What is this isolation boundary? How do we do it? Anyone? Language-based isolation. Puzzled here. Okay, did you guys watch the lecture? Raise your hands who watched it. 2 people. Then it's probably like, what do you guys want to do? You want to go over it again, or just forget about it and move on and do something else, or like it's a choice. Like I don't have a specific kind of like opinion on that. I can go over it again if it makes sense, if it's interesting, or we can move to something different. Because my today's lecture consists of 2 parts. I wanted to finish Redleaf, kind of explaining how things work in Redleaf. But if you didn't watch the lecture, you don't know the first part, so it doesn't really make sense. Or we can just completely switch gears and like take a look at how Amazon uses isolation in their AWS cloud, which is also fun. But I don't have that much to say about it. But okay. So probably it doesn't make sense to start halfway, right? Because if no one understands what's going on, then probably doesn't. It's not really relevant, right? They just a couple of key points. So okay, let's just move to the other one. Like we're not going to talk about fault isolation, just doesn't make sense. Let's then talk about it will be probably short. It will be short, and we can like stop share. Maybe let me reshare the slide deck. So one thing which I wanted to talk about, like kind of as kind of a not a bonus, but something more meaningful for you guys, is how, like, remember I spent some number of lectures talking about isolation and why it's important, how it will prevent specific exploitation techniques, and how it will make our systems more secure. And one interesting thing is that how is this isolation just my kind of daydream, or really is it deployed in anywhere commercially in industry? And it turns out that yes, so people in industry, especially people who run big clouds like this AWS, they kind of took it seriously, and they had resources, and they built a somewhat kind of elegant system which allows you to also improve security of this AWS cloud, as well as like improve performance, and it's in a way very elegant. So and I picked this specific example as one example of isolation. I'm pretty sure that the similar examples exist in people who build cars, so in automotive industry as well. There will be some techniques in the avionics as well. But let's just try to do AWS cloud. So, okay, so the architecture is called Amazon Nitro. I don't know, did you guys hear about it? Never. Okay, so Amazon, like when you really like, and this is how the story goes. So Amazon, when they started their cloud business, they relied on the Zen hypervisor. Remember, we talked about Zen. So who can tell me what it is? Like, how does it work? Real quick. What virtualization technique it uses? Power virtualization, but do you remember how it works?
There's like a thin, like kind of like hypervisor layer below the operating system, and above it, there the operating system runs in a was it like the ring one or whatever above it, and along with like and there's like the main sort of
It's called the domain.
the domain
Yeah.
that kind of like allocates like the drive.
Like manages resources by systems. Okay, I think you're there, but let me just repeat what you said. So Zen is implemented as a tiny microkernel. Kind of think of a x86 kernel. It boots on bare metal and boots into like its own main function. But really, it's just a hypervisor. What it does next is that it boots a Linux kernel, which uses originally, which was using part virtualization. So I will draw my kind of zigzag pattern here. And this domain is a Linux kernel, or it can be a different kernel as well, but the default is Linux. And it's called domain 0. And this domain 0 is kind of like a privileged management domain. So essentially, this domain runs real device drivers which communicate with real hardware. And the way Zen allows this domain to access real device drivers is it uses essentially PCI pass-through mechanisms. So essentially, it allows like there is some virtualization of a PCI bus going on, but really at some point those device drivers in the Linux kernel, which boots on top of Zen and runs, it can either run and this can run in a traditional Zen. This runs in ring 0. This runs in ring 1. So it's kind of protected. The hypervisor is protected from the domain 0, and the user level of domain 0 runs in ring 3, right? And so essentially, and then like whatever, if you have your cloud services, like you have your cloud stack running somewhere, essentially the cloud stack, let me just disable my phone for a sec. The cloud stack can send administrative commands, kind of like this, to like over the network, for example, to this, and there will be like some management stack running here. I don't know, like part of Zen is something what is called Zen Store, and like XS is another daemon, XC or Zen command, and those will kind of like communicate together and create additional domains, which again, in a canonical case, will be virtualized. So let's imagine this will be a Linux, and it will run your whatever Apache and whatnot. And in a more advanced scenario or later on, it can actually use VPX on the root. So this is VPX hardware assisted virtualization. And again, it can run like something like Windows 7 here. And it will have its own rings here as well, right? But everything called communication, you should have your cloud stack go through those device drivers, goes to Linux domain 0 Linux kernel, and then this creates other domains, right? That's a reminder how Zen works. And this is how they started. So essentially, when you were paying them money, you were specifically getting something like this. This is your slice of the system, and that's your Linux instance, which runs in a cloud. Zen implements scheduling. So strictly speaking, they can run you like domain 0 and domain those are called domain user domains. They kind of like context switch, so then implement scheduling. If you have some specific government or licensing requirements, you may might implement a policy that, you know, this, for example, this VM will never be scheduled on a CPU with any other VM. So kind of like to prevent side channel attacks, right? They agree with this? Okay, and this is how they were running, and they made like billions on this. That's their Elastic Cloud, AWS, right? And it's all fine. So here is the picture of the same architecture on my slides. Let me just quickly. So it's exactly what I was just talking about. Sorry. So essentially what we have here is roughly speaking, like unmodified virtual machine, like Windows, for example. This one will be using VTX. It has a virtual device driver. Remember, Xen implements this front-end, back-end split. And this virtual device driver communicates with a backend inside domain 0. So this one is a domain 0. Maybe it's, I don't know, they didn't give it a name, but this is a domain 0. And there will be some kind of a bridging architecture to go to talk to the real devices and stuff like that. And this is unmodified. VM will be using VTX, paravirtualized, like Linux kernels and others will be using the same idea. Virtual devices will be talking to this domain 0. And essentially, like everything as I was discussed, and like some management applications are running inside domain 0, right? So that was AWS, and it's still there, or partially, but it's going away, because AWS came up with a different architecture. So what do you think is the problem with this one from a security standpoint? And actually from a performance standpoint as well. We talked a little bit about it when we talked about Xen, but maybe let's just think about it for a sec. Like when I say security, you probably should start thinking, okay, how this can be attacked. So how? Yeah, so you can find a bug in a hypervisor code. And roughly speaking, this Xen, it's larger than x86. So I don't remember the numbers exactly. But roughly speaking, like easily 30 to 60,000 lines of code, like different architectures, ARM, x86, support for VTX, stuff like that. So not fun. Can find a bug, and there were bugs in Xen. There was a development, another company, people who were involved in a Xen development, they wanted to ship a product which was called Chromium. So essentially, the idea is that when I open a web browser on my Mac or my Windows machine, it opens up in a completely new VM. And it's so transparent to me that I don't even notice, like everything is stitched together. So we have similar products, like now you can start a Windows VM and then it kind of merges the windows of the Windows VM with my native GUI, which I run on Mac. So I don't even notice which program runs where, but it's kind of like, it doesn't work that well. So like I used it on Linux a couple of years ago, it wasn't fun, but there is like, but the idea was to kind of implement a small hypervisor like Xen, which kind of sticks itself underneath your main operating system. And if you open like some security critical application like web browser on a website which you don't trust, or maybe which requires a specific levels of trust, it runs like that. Not sure that they did very well, but the idea wasn't super bad. And they were developing something what they call the micro Xen. They realized the fact that there might be bugs in Xen, and they said, okay, we'll strip it down to a very minimal hypervisor, micro Xen. Right? So that's one bug. Excellent. So what else? How else?
Top zeros.
Correct. Specifically.
Some privileged things are going on very intricate, I think, because it's managing the VMs.
Correct. So you can find bugs in this Xen store, in this XC. Not exactly sure that AWS uses them. They probably rewrote their own, but still probably equivalent. So you can find bugs here. And interestingly enough, remember that every VM communicates with the device driver before like if it's a network interface driver, it's called a netfront in exam terminology. Netfront, it's a front-end driver for the network. This one will be netback. And then this one through some kind of a bridge talks to a real, let's say, Intel IXGB driver, which talks to physical hardware, right? So every VM will have this front end, which will talk to a backend here. And obviously, if you find a bug in a backend, then you own the entire platform between like, even if you have like some different tenants from different domains, you know, which potentially share the same machine, you can then like kind of like attack everyone, right? Agree? So I guess they were thinking along the same lines, and there was a line of academic work from, again, a person who was involved in Xen development, which was kind of like actually multiple academic lines of work, which were saying that let's tear this domain zero apart, kind of like instead of running it as a single VM, run it as collection VMs, like one for network drivers, one for disk drivers, one for management stack. So it will be like not a single domain zero, but rather like a bunch of those, right? Like one for network, one for disk, one for management. And then at least you say management. At least you say if you find a bug in a disk, you cannot immediately, maybe it depends on how, like, if you can access to the disks of all VMs, then yes, that's bad. But maybe you like roll out another level of craziness, and you say, look, each VM will have its own backend VM, backend driver VM, but then maybe there will be like yet another VM which will really connect to the disk. And so the connections will go like from here to the disk, from disk to the VM, kind of along those lines, right? You see how it can be done, right? So that was attempted. Why do you think it's good or bad? Well, it becomes more of a distributed system, which is good in terms of security because you gradually introduce more and more isolation, right? Because you say if you find a bug in this disk driver now, you may be like completely halting the traffic of this specific VM, but in order to affect all VMs, you need to yet stitch another bug, find another bug in a disk driver, which talks to the physical hardware. So this story kind of like, it's nice. It's kind of this microkernel style story, which everyone wanted for years. So in terms of security, it goes well. However, in terms of performance, you need CPUs to run all of these VMs, right? And maybe even like what I want to say, sometimes move data across, like copy data across. Remember my story that in an ideal case, I want to have zero copy data, right? So, and because if you don't have zero copy, then you might be copying from here to maybe even to the kernel. Sometimes this is zero copy from this kernel to the kernel of a disk driver, from the disk driver to this disk driver, and then finally a DMA to the disk, right? So it's kind of like longer. So like non-trivial performance overheads, right? So if you wanted security, it was probably possible, but not ideal, right? Questions?
Pointer application code for ARM 8.0. This might not be related to this.
Yeah.
So they are saying, okay, we have a function. So when I am loading this code on the stack, so we can use like specific tag instruction to like make it a cryptographic key stored in like some register hardware. So and this kind of like cryptographic thing should be used for like point. Remember we saw like pointer related thing before.
You lost me a little bit. So I had slides on ARM pointer authentication. I decided not to teach it because it's one of the most involved schemes. There are some more involved schemes, but ARM POC is like, it's as you say, you have to create a signature with a signing context, and then when you will be using a pointer or something, using something, you will verify the signature, but you have to recover the same context. And typically it involves managing some metadata in memory. So if you remember my story about Cherry hardware capabilities, so roughly speaking, what ARM pack is doing is that if you have a pointer, you can kind of sign it, which means that if the attacker changes it, it doesn't match the signature. And this pointer points to an object on a heap. Sorry, you probably can't see this, but this is an object on a heap. And then essentially, at this point, it's kind of similar to Cherry. So you say, look, it's kind of like a pointer, and Cherry implements it in hardware. And attacker cannot change this pointer because there is no way to do it on this hardware. But PAC allows it to do it on top of ARM. But there is a lot of software overhead involved in PAC. So you typically have yet another metadata table where you say, look, for this pointer, I have to like use some kind of a hash function. Or, I mean, if you don't want to use a hash, then this table becomes very large because for each pointer, for each object in memory, you will have to maintain an entry. So typically people build a hash table. If there is a collision, you handle it somehow. But literally, like it's to like you have to like access this thing, recover signing context for this, then try to decrypt the pointer or verify the signature, and only after that allow the access. So, and it's like a sequence of like 5 or 6 instructions before the pointer. And when we did the study, it was kind of performance was kind of horrific. So it's like if you protect everything, then it's more like maybe like at least twice, and we can come back to it. I can show you after the class the slides. So, there are multiple ways to use PACs. It's a very flexible scheme. You don't have to build exactly that. You can build different protection schemes. You can build, for example, only control flow integrity, meaning that when you call a function, you know that when you return, you know that this return is allowed. So that introduces much less overhead because calling and returning for indirect, like returning of course is often, but calling an indirect function is rare, so it's fine, right? But for protecting every object on the heap is tough. So PAC, typically when people talk about PAC, it's kind of like, you're right. So what you were saying is that what if instead of like running those in individual VMs, we will, on the yellow. I already have yellow. I wanted to say that you can maybe introduce isolation. Remember my story about K-split, my work in K-split, where you say, look, you can, it's another lecture, which was on Monday. I didn't even ask if you watched it. Okay, sorry, didn't want to offend you guys. But it allows you to essentially isolate device drivers within the kernel, and PAC can be used to do that. So that's one way to go about it. You say, look, all these backend device drivers will still run inside this DOM0 kernel, but they will run in isolation. And it kind of, I apologize, that's actually a very good comment. So despite the fact that Zen people went this way, and the reason for that is that back then, there was no lightweight schemes like PAC. And I say lightweight, it's not really lightweight, but at least like assume lightweight. There was no Cherry, no PAC. It was like 10, 20 years ago, 15 years ago. And so for them, like using page tables and paravirtualization was the fastest way to go about it because there is no overhead. You run at native speeds, but then you only have to context switch and run, and there will be like typically a Linux kernel here. Although Zen had a project which they call the mini kernel, which allowed you to run these device drivers on top of some very, very small kernel, which one can call a library kernel or library operating system, right? But today we have like more of those hardware isolation mechanisms, and you can start thinking about like carving out parts of a real Linux kernel into those like isolated domains, and then maybe that will achieve the same security benefits as this. Possibly, yeah. So that's a possible approach to do that as well, right? So, sorry, I kind of like answered probably a different question, but nevertheless, like, is that what you like?
Yeah.
PAC is, but PAC is like, if I'm a little bit surprised, to be honest, by the emergence of PAC because of how slow it is, and like, in my opinion, it's somewhat impractical. But maybe there are some scenarios which which can like use PAC in some controlled manner, and then it's practically fast.
So like some small microcontroller chips.
No, PAC was essentially designed probably to partially, like there are multiple ways. Maybe one thing is to support address-based sanitization, meaning if you have a unsafe access, it will catch it and say, okay, you have a bug here. So you can, if you run it under fuzzer, for example, you compile with PAC, you pay a performance price, but maybe you already paid price for fuzzing, you do the fuzzing thing, but then any access outside of this object immediately triggers an exception, because you can say trigger an exception when the signature doesn't match, and then you're immediately catching this fuzzing at the level of fuzzing, right? So it's kind of like a very carefully constructed address sanitizer, right? But also then later people started using it for isolation, and for isolation it's, I would say, impractically slow, but that's my understanding, but it's still doable, I guess. Okay, this is back to this. Clear? No more questions? Okay, so they tried to do this, right? And like, I don't think that Amazon specifically was trying to do this, but they were probably watching some of this development, right? Because at least one person who was working on this, the paper which was taking DOM 0 apart, one of the projects was called Breaking Up as Hard to Do. I forget the name of the project, but that's the title of a paper. And that person went to Amazon, Andrew Warfield, right? So he probably could at least like have his own opinion. Maybe there are multiple teams inside Amazon. So I don't know if they were doing it, but that's one way to go about kind of improving security of this system, right? And not surprisingly, they didn't go this way. Amazon kind of pulled the trick, a very elegant trick in a way, which kind of wasn't that. So what do you think they did? As a systems designer, what would you do?
In the Nitro.
In what?
In Nitro.
In Nitro.
So they kind of make hardware for all this.
Good. Like you're right. So hold on. Like I was expecting a slightly longer discussion, but good that you know Nitro. Like how do you know it? Because you worked with it. Okay. I'll come back to you in a second. Jared, you had an idea?
No.
It's kind of similar, but in a way, somewhat elegant as well. Okay, then since we're back to Nitro, and the high-level idea that for each of these guys, they build a piece of silicon. So, but can you tell us how it works? Or you? Okay.
Especially I will use my relating to my hardware.
Yeah. Then let me go about it. Then, okay, they made this observation that this domain 0, it runs on the general CPU. It's kind of a case, but there's like layers of software, you can attack them, but also you use those CPUs because they consume some amount of like CPU load, right? And they said, this is kind of clever. So by then there were projects in the cloud world. And one of them was from Microsoft. I forget how it was exactly called. Somehow, no, don't remember at all. But the idea was that you don't have to run all of your workloads on the general CPUs. And instead, you can start plugging cards, meaning if you have a card, which you can manufacture, maybe it's a network interface. Then you say, look, maybe if I run my VM, if the card implements, remember I said that cards have this capability, it's called SR IOV, a single root of IO virtualization. Essentially, it's an ability to expose multiple instances of the network card. And essentially they said, okay, look, this guy will get an access to this network card. And the second VM will also get an access to an instance of this network card through this interface, right? That's the device drive for this card, which means that the VM, and I mentioned that in the past, so there's like DOM user VM, DOM U, can directly over PCIe kind of hardware bus, right? Talk directly to the piece of hardware, right? And then it has like a network interface, goes to a switch, right? Then instead of like running something inside domain U, inside domain 0, like your backend interface, they say, okay, let's run it on this card. It's a piece of silicon. I mean, I don't think Amazon releases the software stack. Like naively, you can imagine maybe it also runs Linux, to be honest. Or maybe some other operating system. So it's like there will be an ARM CPU and maybe some additional, because ARM allows it and it's nicely, maybe you can run some pieces of silicon to accelerate some network processing, maybe like matching rules, stuff like that, right? Then roughly speaking, it allows you to remove bits of domain 0. So what Amazon started doing is that they acquired a startup, and this startup was able to provide, instead of like buying a card from Intel or anything like that, they said, okay, we have enough resources to develop our own silicon. And it's kind of nice for 2 reasons. They said, okay, we're going to develop a network card. We're going to develop an NVMe card, which will provide some local NVMe storage, same idea. So SR IOV, and essentially it will directly connect to the VMs like this here, right? So now this VM has storage, has a network stack, and this storage, that's really here on board on NVMe. The question how do you instantiate? Like imagine it's your local storage. What if it has some state? Like remember that in Amazon, there's multiple ways to access storage. And majority of the of your real persistent storage is sitting behind the network storage. So they have I forget exactly the name, what is it? Elastic Block Store, I think it's called, right? EBS. So which sits on some servers and you access it over the network. And that's where you have your terabytes of data. And this EBS you access, I think, through the, I don't know if they have a separate card. They might have a separate card, which actually implements EBS capability specifically. So it's kind of like a glorified mix between network and storage, or maybe they go and collocate this EBS with the network card itself. The network card itself is called Elastic Network Adapter, ENA, right? And it's either these two or a single ENA and then ENA/Elastic EBS storage access, right? So typically your real storage is behind the network card, and this might be even clean when you boot it, and it's just simply a local stash of storage, which you really need for some, I don't know, temporary data. Like if you do database joins, maybe you upload your tables eventually here, do the joins locally, and then once in a while switch back to EBS, right? Okay, this is cool, right? But still, who controls how to boot VMs and stuff like that? Who do you talk to when you actually want a new VM on this host?
There should be some custom.
They did build a custom hypervisor. I'll talk a little bit, but imagine they have their cloud stack. I don't know what it's officially called, cloud stack. Some, some piece of software where you sign in, have credentials, you click a button, it charges you. And then it has to actually say, look, I really want to create a new VM on this physical host because I believe that this has enough compute resources to run this VM, right? So, and they did put a tiny hypervisor. And it's actually KVM based. They ditched Xen completely. So we'll talk a little bit in a second. But really, they said, okay, but what about the KVM is really if you ever looked at it, maybe you never. So it's a kernel module. It doesn't do much. So it's kind of processes an exit condition because you're running inside the VTX non-root. And once in a while, maybe like this guy kind of phased out your memory, you exiting with a condition, and then this guy typically upcalls and does something elsewhere to like figure out what to do, right? So it's kind of like a very minimal thing. And what those guys did, like instead of running, okay, like maybe let's talk a little bit about KVM. So KVM, like I'll make a picture here. The way KVM works is that in contrast to how Xen works when you were booting into Xen, here you boot into Linux, right? And then Linux is just has a kernel module, KVM, which it loads like any other regular kernel module. Typically, all the management stack, and typically people use QEMU, runs at user level. I mean, they typically, when you do like create a new VM, like you talk to QEMU talks to KVM, KVM initializes the VTX container for this new VM. And then I don't exactly know how, but they jointly load the kernel, let's say Windows. And then because the thing is here, but KVM doesn't really doesn't do much. So for example, like in a manner similar to how we were thinking about devices, like KVM, like really there's another class here, it's called Advert.io. It's kind of similar to backend and frontend in Xen, but like more general, and it's called Advert.io, and then you talk to a real physical device over this Advert.io thing. Right? So, and of course you say, is it, in terms of security again, how good is it? Like what's the attack surface, where you can find bugs here in this KVM architecture?
KVM could be pretty, can have supply chain balance.
Well, you're right, but KVM is reasonably small. So you're right, it's possible to find a bug in KVM. And especially if it's kind of somewhat layered. But majority of the bugs will be in QEMU because it emulates the BIOS legacy devices. Sometimes you can find bugs in this Advert.io thingy, and like in the device driver of the kernel itself. And the moment you find a bug in the device driver of the kernel, then you own the entire machine because this is not isolated in any way, right? So this is this running there. But you can find a bug in KVM as well, but it's less frequent. And of course, at this point, you can make a decision how you want to get rid of this. And so they kind of like again, not all the details are publicly known, I guess, but the thing is that they said, okay, we want the KVM to do only a very minimal thing. Run it on top of Linux. So there will be Linux here. But maybe don't do any those device drivers should not exist, right? Why? Why is it possible? Because we have SR-IOV, and really what KVM does is just exposes some kind of a PCI bar region for this device, and then it communicates. At some point, what I was trying to get to when the cloud stack says, okay, create a new VM, someone has to give instructions to KVM what to do. Someone even has to communicate to the cloud stack. So the decision they make, instead of running something here, some kind of a cloud stack, and running some device drivers locally here, in this kernel to communicate to the real physical hardware, they said, okay, we're gonna have another Nitro card. So those things are actually called Nitro cards. And they said that there will be a control Nitro card. I forget exactly. I think they call it actually control. And this Nitro control card is actually connected to the cloud. So again, don't get misled. This thing is running something like Linux. Even if it's a different kernel, it's of equal kind of complexity. So, but they send a command kind of to Nitro card, and they say, okay, we want to create a new VM. An interesting design choice which they make, that those Nitro cards are all kind of connected I don't think it's, I mean, I don't know the details of the wiring. So maybe they go through like a local switch, top of the rack switch, but like essentially what happens is that in the back of the rack, they are connected to the control card, from what I understood from their slide decks. Which means that Nitro, instead of talking to the hypervisor, this control card starts negotiating with the storage network and EBS interfaces. It starts negotiating, oh, we are about to create a new VM. So please make sure that you will like carry another SIROV interface, which will show up and will be visible to the hypervisor. And this hypervisor will make sure that this page or whatever will be mapped inside this VM which we're creating. And after they negotiate like whatever, like maybe some partition of this local storage, some network topology on the network, maybe some access control for this EBS thing, only then they kind of over PCI bus, if I understand correctly. So Nitro talks to the hypervisor, which probably means that there is a little bit of a PCI driver here sitting somewhere, like I'll draw it on the edge between the KVM and the kernel, the CTL interface. And like essentially at this point, this is how it signals to KVM to say, do something, like start a new VM. And then at this point, KVM, which manages physical memory, says, okay, I will allocate this VTX on root, will allocate pages of memory to make sure that these pages are running. And I think the boot protocol will be something over the network or something over this EBS store. I don't exactly know how, but it's not clear, but it's not super hard either to come up with a different boot protocols. But essentially the point here is that at least the way they sell it, and it's again, it's a subject of investigation, that roughly speaking, no user process will be running somewhere here or in this, like in this, on top of this kernel to make sure that this VM boots. I'm a little skeptical of this because if they want to boot unmodified Windows, then at least they have to run some kind of a BIOS emulator. They should probably run at least the process, but maybe it's so heavily restricted that even if you find a bug in this BIOS, it doesn't even have system calls to maybe to like, because this kernel might not even have network connection. It talks to the Nitro control over PCI interface, but you can't even like, there is no way to find a bug in this kernel and like get on the network, for example. You can probably game, like everything is kind of a little hazy. So there are probably a possibility of finding a bug, but and like again, but at least like on the surface, it looks that it's hard, right? So and that's what they did. So it's kind of like a nice combination. So I'll show you the slides here. So if before Nitro it looked like that, so this domain 0 was running. They drove it kind of side by side with the Xen hypervisor, which is partly true because it kind of sounds privileged and all this virtual private cloud networking, PBS storage, local storage, kind of driven by domain 0. So when they switched to Nitro, they essentially implement an architecture which looks somewhat like this. So they have a Nitro hypervisor, and then they use this Nitro parts to essentially run all individual parts of like kind of your device drivers, virtualized device drivers on this hardware. So it gives you a couple of interesting properties. First of all, like I talk about it in terms of isolation, right? And we can discuss a little bit more in a second about really whether it's possible or impossible to find a bug, but it also gives them a benefit in terms of performance, because instead of like wasting your general CPUs on running whatever device drivers, now you plug more CPUs, and those CPUs are quite powerful. So those Nitro cards probably run in some cases run like beefy silicon, right? But it's kind of a way to design a system which is somewhat unusual. So it's no longer centered around the general CPU, but rather centered around PCI bus and those Nitro cards, and using CPU in some way as an accelerator, which just occasionally runs something, right? And so I'll give you a couple of, this is like the control paths from one of their slides where the C2 cloud control plane talk to the Nitro controller. Yeah, it's called Nitro controller. That okay, allocated the VM, then they don't show the second step, but they, in some other slide decks, they did, that those guys communicate, on the back of the rack. And then it, gives an output to the hypervisor, and then, over PCI bus, and then, like, those guys are connected to those Niger parts. Just, like how it looks physically is the following. So this is their rack server, and with two Nitro parts. I don't exactly know which one is which. So one is probably a controller, which is probably primary, and another is networking. So be careful enough. Most of them have network ports, but you probably can figure out which one is which. But this is how it physically works, right? So it's interesting how the systems are kind of evolving. In terms of like both security and again performance. So you have a question?
I have a website.
You have a what?
Website.
Website.
So it's a production heavy something. So for the secret reason or downtime, I want to use two different accounts.
Why two?
So that if there is something wrong with this thing, I can support this by other.
Yeah, kind of like for reliability reasons. So
So, but if these things are like hardware specific, the microchips are not similar to other.
wait, but you never see your workload runs on real Intel CPUs, for example, or optics. So, and those are sitting, this is the memory, right? And those are heat sinks defined and directly everything. So this is like a 2-socket machine, I would guess. These are 2 sockets which probably either running Intel x86, let's say, or ARM silicon. So this is where your VMs are. And those are like the rack servers. Typically, you buy those from Intel. And typically you connect to those cloud planes, like the main zero, which runs here, and then it pushes the traffic from gas domains back into the card, back to the port to the switch, right? And here it's somewhat kind of like flipped. So the control plane immediately hits a controller card. Controller cards negotiates with the local, let's say, network cards to say they create another SR IAV interface. And then over the PCI bus talk to the hypervisor, which does run on those real cores, for example, or ARM cores. And then this guy says, okay, I'm like, out of this available physical memory, I will allocate some and will run a VM on top of it. And then it will see one of these SR IOD interfaces. And so if you like, in terms of Amazon makes a point that their elastic network adapter interface has not changed over the generations. They started from supported by 10 Gbps interfaces, and now I think they are supporting 200 Gbps interfaces. Which means that they say, look, instead of like following the Intel path or Mellanox, which has a device driver for every generation of hardware, we somehow guess correctly how this interface would look like. So your VM, which means that this, for example, this runs a single ENA driver, and you can actually use like VM migration, and it can start even on a card, which supposedly should start on a card with different capacity. But they said that they didn't have like the first, like if you know this, or maybe you missed, but this NVMe, of course, it's a standard which covers all, like no matter who produces the flash storage, like, or it's coming from Samsung, from somewhere else, like from Intel, for example, they have a single standard NVMe. So the kernel has one NVMe driver. You don't need a specific driver for like an Intel storage adapter or Samsung. And they did the same trick with networking, kind of. So which is kind of clever. Yeah.
So here, and we have offloading some of the software action and some application specific, like integrated silicons.
Kind of.
These are like application specific silicons that
They are not application specific. They are like just virtualize, for example, network interface. So this SR-IAV allows you to, this guy has enough smarts to virtualize itself. So it runs a combination of software and hardware, mostly probably software, although I don't know the details. To say that, it's almost like you plug one physical card, but every time you start a new VM on a PCI bus, a new network card shows up, and it's almost as fast as the original ones.
From perspective of hardware, it's not that spatial.
Meaning spatial.
The hardware is not, those are general computing concepts. From the hardware perspective.
No, just for a second, I don't know which one is a controller card and which one is a network. It's hard to do. But let's imagine this yellow is a network card. Then this is what you get. So this thing, which probably runs, it has an ARM core, ARM CPU, probably quite beefy. Can virtualize itself and expose this one single piece of hardware as multiple network cards for each new VM which runs on those ports over the PCI bus, because this technology existed. It's not that Amazon invented. It's called SR-IAV on the Intel, on ARM it's called. I don't know what it's called, right? But essentially it allows you to, when a network packet comes and hits the network interface and some silicon of this physical device, it might not go to this kernel, which is Linux, but immediately in silicon somehow route this network packet directly to a VM which runs here. And if the next packet comes out for the next VM, it will route it to the, yeah. And this silicon will allow obviously to do it much faster because you can in hardware programming language like Verilog or something implemented and really gates stuff.
That's what I was a little bit skeptical about. It kind of limits the barrier of creating VMs and things like that. So it's specialized.
Correct. So you might say, okay, so how many VMs you can create? And that's up to them. I don't know what the physical limit of this SR-IAV interface, but it's probably large enough in practice that you probably, most likely as any hardware designer, they do a balanced kind of choice. They say, look, if we have a machine with 40 cores, well, maybe 40 interfaces is enough. But then they say, okay, well, if we can support 40, we can support 128 as well. And that's probably enough to.
On the other hand, previous solutions that we discussed, other solutions, deploy it on a very generic, those has to be beefy actually, but very generic hardware architecture. But for these, we need spatial
Correct. So they chose but the beauty of this design choice is that they control build the cloud. And instead of saying, okay, negotiating with Intel, can you build a card like this for us? We're going to use it. They say, we're powerful enough. We can build the silicon. We have thousands of those machines, not thousands, hundreds of thousands, or millions, probably tens of millions. And they stick this card, build it once, stick in every rack. For them, it becomes a commodity. Right, exactly. And so Microsoft was doing something similar in their cloud, but for performance reasons, because they said, okay, it will accelerate certain workloads. And I have a slide here, again, from their slide deck. Amazon obviously wants to be a player in the machine learning space. They have two CPUs. One is for inference and one is for, what's the second part of the kernel workload? One is training, one is kind of using.
Inference is
what?
Training and inference.
Training? Yeah, so probably this is training. They have two CPUs, they call Trainium or something. Training and in something for inference. And so here they build a very beefy, I'll show it, it's like an ML accelerator, which is, I don't actually know, are they showing the card here or probably the card? You think it's a blade? The whole thing, the whole blade, right? Probably. So I don't know where the nitro cards here, but I don't know. The way they showed, I took it as those are the nitro cards. But essentially, the way it's the system sees it is that, like, if you run your VM here, you talk to everything through a PCI bus and go to the network. You can go to local storage, this and NVMe thing, which I was drawing here. And on other, like, typically PCI buses have multiple hubs. You know, you have another network and another storage, and then the training chips, the Trainium, or collection of those. And I think the way they advertise it, they said there's like 16 instances of those. I don't know what this orange communication line is, but they can communicate between each other. They have high bandwidth memory as well, but that's essentially how the system, like, it's everything is over PCIe.
AWS?
It's in the AWS. So, but essentially, I forget what I meant to say. What I meant to say is that in practice, in other presentations, they advertise some amazing capability of those network interfaces. So, for example, they implemented a multi-pass TCP, which is kind of cool because if you have a contention in the network on the card itself, they know the state of the network because they control it and like measure it. They immediately send a signal to the card and choose a different pass, and then like it immediately balances the traffic. And even like the network, the packet, individual packets don't choose the same pass from the network. So again, it's a nice kind of like high integration example when they say that it's not just, I mean, it started from the point of security, and then, you know, in practice, it's also probably a very beneficial from the point of performance. And other cloud providers, like I was saying, the research, I don't really know what others are doing, but there was a research work from Amazon which was doing similar tricks where they were using the PGAs here, and majority of it was a cloud which was using pre-programmable hardware, which is the PGAs. Some workload was running in main CPUs, but then the majority of the workload was running in PGA cards, which were somewhat similar to this connected. And even between the individual servers of the rack, they had network connections coming out from the rack that allow them to like do fast communication between those cards. Okay, so we got how it works, right? It's kind of cutish, right? Because actually, didn't expect that it would take me so long, but probably I wasn't smart or wasn't very fast. Okay, security story. So. Okay, like it's a good kind of question now. Okay, did they achieve a significant security benefit or a gain? What's the attack surface here? Let me come back. So like on the surface, the way they advertise it, okay, it's hard to probably see from this thing, is that it runs a very tiny Nitro hypervisor, which is KVM based, so it puts it to Linux kernel, but maybe it almost never touches the rest of Linux. So it does like runs and like, almost never does. And then each of those are connected over PCI bus to those Nitro cards, which are running like. Okay.
Have like newer formats, right? So it might not be tested like only, there might be some.
I agree. So essentially, what you're saying, and that's my kind of guess as well, is that despite the fact that they push backend drivers from Xen into the cards, the logic of the same device drivers like exists there. So which probably opens up an opportunity to find bugs in the Nitro cards. So if you scroll online and quickly do a search on LinkedIn, you see that there are people who advertise themselves as developers who are working on those Nitro cards, right? So which means like again, there's a huge chance that nothing super magical happened here, and it's the same kind of Linux, similar to what we were running in, say, domain 0. Who knows what kind of isolation? Do they use PAC here? So next time they interview you, you say, like, do you use any of the isolation technologies to make sure that this SI logic of this SRIOV virtualization is somehow isolated between individual tenants? We don't know. So they kind of achieve bits of security through obscurity. Probably a good security researcher will will construct an argument how they can like go about it, exploiting bugs in those Nitro cards. The way as Amazon spins it, that is like it's more isolated. In practice, really semantically, it might not be isolated at all. And really, in order to achieve any isolation, you really have to do something with the software stack. But who knows, maybe they build a new operating system. Maybe it's in Rust, like my wonderful Redleaf kernel. So it's like immediately eliminate 70% of vulnerabilities. You have to very carefully scroll through those resumes. And if there is a correlation, Nitro card, Rust, then you know for sure that those guys are Rust developers, right? Maybe they did something more clever. Maybe they like from the cleverness of how they build everything, or maybe it was really driven by performance. Maybe they did something like really redesigned the software stack on those cards, and it's really carefully, like super minimal, hard to find a bug, right? But really, yes, those Nitro cards are clearly like a target of attack, right? So essentially, there is like two things. Like if you're outside facing server, then you can probably, like if, as you said, you're running a website, then you just go straight from the network card directly into this VM, find a bug in this kernel, and then you own the tenant's VM. But you still don't own the cloud. But you can, like, if it's your first step of attack, but you can as well be on that cloud by renting a VM. But so there is one attack when you attack the VM of the tenant and like steal secret data of the tenant, which is like, I'll draw here. Or maybe if you really need to, you can try to attack the network, the Nitro card, and then maybe gain some additional privileges in this cloud. Or they say that all the APIs to the Nitro cards are like logged, authenticated, stuff like that. So it's probably harder to like to exploit in practice. Amazon has yet another example of an interesting isolation solution. Let me just, since I still have 10 minutes, it's something what is called Nitro enclaves. They specifically wanted to, I will erase a little bit here. They wanted to make sure that they understand the fact that their tenants are running like stock, maybe somewhat hardened, but stock software stacks, right? And so if you have a KVM hypervisor, okay, maybe that's close to bulletproof because it's very, very small. If the tenant runs a VM and it's in, let's say, outside facing VM, if the attacker finds a remote vulnerability in the Linux kernel, which runs here, which is not probably uncommon, especially if you have resources and carefully look at the Linux kernel, it might be most likely either in an ENA driver itself, but unlikely because it's reasonably small, but most likely somewhere in the TCP IP stack, or maybe even in the application logic itself, you know, because who writes those applications? It's us, right? So tomorrow you're going to go work for Amazon. You could be working on this maybe. I mean, any company rather, right? So for Amazon, you're going to be working on ENA drivers, but you can find a bug here, right? And what if there's like a secret, like for example, like whatever, some kind of like authentication key, which is critical because if you steal it, you can steal all the data of whatever 23andI, whatever the company is, like, which does genomic analysis, whatnot, right? So they came up with another interesting technology. We've heard of enclaves, and I didn't cover SGX enclaves in this class, but it's something somewhat similar. So they said, okay, in Amazon Cloud, you can request something what they call an enclave VM. So essentially, the primary VM can ask the hypervisor to create out of its own resources, I think, or it doesn't matter, out of some resources, create an enclave VM. And in some way, this enclave VM will also run some kind of a Linux kernel, at least as of today. Maybe they later will allow it to run something smaller. But the point is that it will not have connection, no device drivers, nothing. So it will not be connected to the network. It will only have one connection through a vSocket interface, vSock. And it's part of this vSockets, virtual sockets to connect VMs. It's part of the VirtIO kind of architecture in Linux. And so the only kind of outside channel is this vSocket interface. So if you really run an application and instead of having this key here, you place it here, then you kind of build some kind of an API which says, okay, like sign or something, some kind of this operation, right? But just an API, and that you channel to this enclave, right? So this way, and it supports kind of memory boot and everything. So enclave, like it might be even like on some hardware, it might even support memory encryption kind of underneath the L3's last level cache. I don't know how, if you know what it means, but essentially that's what they did. So this is the Nitro enclave. So yet another, a slightly different spin of isolation, because I keep saying isolation, isolation. And you say, okay, maybe he doesn't like, he just wants to talk about it because that's his research. But my point today was to show that those guys care as well. And that yet another example of isolated approach is this. So the customers themselves, they assume that their software will be exploited because it's buggy, but they still want to run some super critical parts of their workload in yet another isolated VM. And supposedly it's harder to exploit because it's like, you have, in order to get this one, what do you need to do? First, you exploit the primary VM, finding a bug, and then what?
Access to the system.
Yeah, so then, if I understand correctly, you really need to find a bug in the vSOC or inside the application logic itself. Maybe there's some kind of a bug says, so release the key, and it just sends you the key back. It happens, right? So yeah, so it's just interesting that this is how they advertise it. So essentially, they say that this instance B creates an enclave, and the only communication is vSocket. Again, the point here is that don't immediately buy into this like marketing stuff and first like look at it carefully. And so this is the there's a company Trail of Bits, which does some security research. Yeah, I actually don't know what the company is doing, but they wrote a blog post in which they discuss the possibility of attacking those enclaves. And there is at least like, there are some connections to the hypervisor. So essentially, you can maybe find a bug because I think hypervisor manages those vSockets. And if you find a bug in the vSocket interface, it's possible. If there is not sufficient isolation between caches, there is a possibility of mounting the side channel attack. At least they talk about it. Obviously, there's also some kind of like an entropy, this kind of assembler, or know what it stands for, implement some randomness and stuff like that. So essentially, again, be more careful about what is running. And like, there is probably a possibility to find a bug in this stack as well. Still interesting. Okay, so that's my last slide for today, I guess. So any questions about Nitro? We're gonna finish the class. Okay, sorry, a couple of things. So like projects, right? So let's make them due on the last day of classes, right? So that's what's the date? Right? What's the date? I don't know when the classes end, but pretty sure that they end.
What will you submit?
Submit me a description of your project. The best we can.
Yeah, I know the detail of this.
Yeah,
There is one beginning time this PhD.
yeah, cool. Yeah. So that's a popular company. They hire.
It is just passing all this.
Yeah. It just like everything deserves a deeper dive, kind of like you cannot magically solve all the problems, right? So, but I wanted to say is that like we talked a lot about isolation. I wanted to come back and talk last day of class on Wednesday. So like when is the classes? Maybe it's this week. The last day of classes is there. Let's say okay, whatever, by Friday. Let's say by Friday. I mean, I'm lenient obviously. So like if you're super duper late, but still. But I will talk about performance. We will talk about something what is called kernel bypass, and essentially the idea of how to build systems in which are fast. So like, and what directions are there. Okay, cool. So then, thank you. So I'll see you on Wednesday then.